Hey everybody, hope we're all doing okay. This is Mr. Krowski. Today we're going to talk about chemical versus physical changes, chemical versus physical properties, and we'll wrap it up with a little discussion about metals, nonmetals, and metalloids, which kind of go back to kind of classifying matter and looking at what type of elements we have on the periodic table where they're located. So let's start with chemical and physical changes and properties. We'll start with the physical ones first, I think. So a physical property, these are things that you've probably observed these and have looked at physical properties more than you realize, whether it's in lab or just in general. But a physical property is a property that can be observed without changing the composition of the substance. So the identity isn't changing of your substance when you describe this, okay? So if you are wearing a red shirt, I don't know, and you say that your shirt is red, that's a physical property of that shirt, the color of that shirt. By you saying that the shirt is red, it's not changing color, right? It's not changing from cotton into some other material or polyester into some other material. It's staying the same. The identity is remaining the same. So you're just observing something about matter, okay? That's what a physical property is. A physical change is when that matter changes form and you change the extensive properties. Extensive properties have to do with how much you have. So length is an example of an extensive property. Okay? So if you have a ruler, which is 12 inches, and you cut it in half, well, it's not 12 inches anymore, right? So the length of that ruler is an extensive property because you change how much of the ruler you have and you're changing that property. Same thing with mass. Say something is 2 kilograms and you take some of it away. Well, now it's not 2 kilograms anymore, right? So that's an extensive property. Examples of intensive properties are, like I just mentioned, color. If your shirt is red and you rip your shirt in half, well, it's still red. Okay, that didn't change. Density is another one. That's a common mistake. So density is an intensive property. It's that relationship between mass and volume. So if something is, like water has a density of 1 gram per milliliter. If I have a drop of water, it's 1 gram per milliliter, its density is. Or if I have 2 gallons of water, it's still 1 gram per milliliter as the density. Okay? So other intensive properties besides color and density that you can look at kind of vary. You know, you can look at, I don't know, the texture of something. That could be an intensive property. There's like how well it conducts electricity. That could be another intensive property. There's a bunch of them that you could look at. You just want to ask yourself, if you change something about, like if you change how much of that substance you have, is that property changing or not? If it is, like length, then you can say it's extensive. And if it's not, then it's going to be intensive. There are way more intensive properties than extensive properties. All right? So, last thing on this slide. A physical change is occurring when you have the same identity before and after. Okay? So if you do take your shirt and rip it in half, well, it's still a shirt, right? Half of a shirt and half of a shirt, but still a shirt. Still made out of cotton or polyester or whatever. We'll look at a couple more in the next slide here. These are some common examples. I have some on the bottom here you guys can see. So boiling, cutting, freezing, melting, breaking, dissolving. These are all physical changes. Dissolving is one that always tends to get students. That's a physical change. We're going to look at the animation we did the other day, the other video lesson that we have here, and we're going to look at that same sugar cube and that sugar cube dissolving. So if you remember the formula for that sugar cube, all the molecules were C12H22O11. So we're going to watch it dissolve. And remember, a physical change is when the identity remains the same before and after. So before, you can see the formula, C12H22O11. Now it starts to dissolve. What's happening to that formula of sugar? Well, nothing is, right? It's still staying as C12H22O11. So because the formula is the same before and after, the identity is the same before and after, these particles are just moving further apart with the water molecules surrounding them. That is a physical property. Okay, a physical change is dissolving. Your identity is the same before and after. If this somehow dissolved and the formula changed into something else, then it would not be a physical change. And the fact that it doesn't conduct electricity, that's a physical property. That's an intensive property that I just kind of mentioned. Okay? And this is easy. Any change in state is physical. So boiling, right? You're boiling water. Well, what's the formula of water in the liquid state? Well, it's H2O. When water boils, turns into a gas, what's the formula of water in the gas state? Oh, still H2O, right? It's just a different state of matter. If you froze the water then, okay, well, water as a liquid is H2O. Water as a solid, what's the formula for ice? Well, it's H2O. The identity is not changing, okay? I'd say change of state students tend to understand pretty well. Dissolving is one that tends to get them, though. So keep that in mind, that dissolving is a physical change. Any change in state is a physical change. A lot of other things that you're going to look at are going to be chemical changes. So you can see those. I already have them listed here for you. Okay, a chemical property, kind of goes along with chemical change here. A chemical property is a property that describes how a substance reacts with other matter. Okay, so we can safely say that if you light something on fire, then the formula of that substance is going to change, right? So we can say flammability is a chemical property. And then once something is lit on fire and the reaction concludes, then we can say that that matter has gone through a chemical change, all right? So in order to observe a chemical property, the composition must be altered. That's different from a physical change and a physical property, right? Because those physical changes, you keep that same identity, that same formula. For a chemical change, that has to be altered. So sugar before heating, during and after, there's clearly like a color change here, and there's clearly a change in formula from before and after. All right? Let's take a look at some other ones. Some examples are flammability, obviously, like any combustion reaction. We'll look at combustion reactions and reactions in general way down the line, but we'll be able to look at some of the products of those. Reactivity, any chemical reaction that occurs, like putting a piece of metal in acid. You're going to have a gas being produced. You're going to have some other things occurring that change the formula of that metal. Oxidation is our fancy term for rusting, and if something is biodegradable and it breaks down on its own. All of those things involve a change in identity. Now, sometimes, like without knowing a lot about formulas and this and that, it's hard to like know if the formula is actually changing. Is the identity actually changing? So what we have is a list of things that you could look for that pretty much it's a dead giveaway for a chemical change. You have to know these 4 things in this list. And memorize these and know these inside out, upside down, okay? So know what these 4 signs are of a chemical reaction or a chemical change, and then you're pretty much good to go. It's pretty easy from there. So the first one is a change in color. Now this one's like most of the time, all right? So a change in color can sometimes be a physical change. An example of that would be what we talked about in a previous lesson where we were making Kool-Aid. All right. So if you make Kool-Aid, your Kool-Aid mix in your water, and you dump the Kool-Aid mix in, clearly there's a color change there, right? But that color change was because something was dissolving, and we just said dissolving was one of the common mistakes. Dissolving is a physical change. So changing color where you're going to have something like that, like something dissolving in something else, that's not going to count for a chemical change. That is just a physical change. Okay. But let's say you rusting. We just said that was an example of a chemical change. You have your nice shiny piece of metal beforehand, then after it rusts, there's a definite color change there. Like a chemical reaction causing that color change, like that's what we're looking for here. All right. Bubbling is another one. And I'm not talking about, keep this separate from the physical changes, right? Like, of course, when you have boiling and evaporation, you're going to see bubbling. But that's because you're heating a substance up. Right? In this case, we're talking about you mixing 2 things together and it starts to bubble. Like you drop a piece of metal in acid, you're going to see bubbles there. Okay? So that means a gas is being produced. You're not, this bubbling isn't happening by you heating something up. That just goes back to the physical changes. Okay? Formation of a precipitate's another one. You need to know what this word means. That's why I have it underlined here. I have a little video clip on it in a second. But sometimes a chemical reaction will give you a precipitate. Which is an insoluble solid. So insoluble means does not dissolve. And obviously the state of matter is a solid. We'll look at that video clip here so you can see what a precipitate looks like. And we're going to do a lab when we get to our chemical reactions unit where we look at forming a lot of these precipitates in some different colors. So let's watch that clip and then we'll go on to the the last sign here of a chemical reaction.
Adding very pale yellow sodium iodide to colorless silver nitrate produces a very pale tan precipitate.
All right, last one is a change in temperature. Now again, this isn't you putting a pot of water on the stove and heating it up. All right, this is a chemical reaction occurs. I keep going back to the metal in acid, because if you put a piece of metal in acid and you feel the container that it's in, it actually gets warm. There are some reactions that get cold, endothermic reactions. So a change in temperature or energy is a definite sign of a chemical change. Something's going on there. All right, look for those 4 things. If it's not any of those 4, it's probably a physical change. So a couple examples we can go through. Water is being heated in a microwave. What do you think, chemical or physical? Well, that one's going to be a physical change, right? You're just heating up water. It's still water, right? It's still H2O. Water freezing. We said freezing was an example of a phase change, which is physical. And iron nail rusting. What do you think there? We already saw that on our slide. Okay, rusting or oxidation is a sign of a chemical change. Gas is being compressed with a pump. That just means you have gas particles. Okay, here's your pump. This is going to be a horrible drawing. There's your pump. Okay, here's your gas inside of it, right? And there's like a plunger or a piston here. Okay, and you're pushing down on that. Okay, and you push down on that gas, and all the gas, instead of taking up this much space, maybe that plunger gets pushed down to like right there. You know what I mean? And now all these particles are in that location. Well, you're not changing what gas that is, right? If it's oxygen or nitrogen or helium, it's still oxygen or nitrogen or helium. So since there's no change in what that gas actually is, the identity is the same. So you're talking about a physical change there. You're just changing the volume. Silver coin tarnishes. Tarnishing is like a fancier word for like oxidation or some reaction going on. So if you see tarnishing or tarnishes, that's a chemical change. This one's easy. A lump of coal burning. Anytime you see the word burning, you're thinking flammability, combustion reaction, you're thinking chemical change. And we already talked about this, table salt dissolving in water. One of our common misconceptions here, dissolving is always physical. Okay, to wrap it up here, let's look at metals, nonmetals, and metalloids. If we're in school, I have a lot of these like on my desk, or I could show you guys some examples of metals versus nonmetals. So think of things like aluminum foil you have in your house. It's obviously a metal, we all know that. And think of what properties it has. And then nonmetals are the opposite of that. Okay, so metals tend to look shiny, right? We say that they have a luster to them, so that's our fancy vocab word there. When you can hammer it into a thin sheet, okay, and you should make sure you know what these terms are, that's malleability, or how malleable something is. So can you hammer it into a thin sheet? On the same line of that, we have something called ductility. Metal is used in wire for your house, okay? So you have a lot of copper wire in the walls of your home. So being able to pull the metal into a piece of wire, that is how ductile it is, or the ductility of something. Obviously, metals conduct electricity very well, and I have a clip to show you about that, which we're going to take a look at right now, actually. So metals conduct electricity very well because they have this thing called a sea of electrons. And we're going to look at that a little bit later in the course, and in AP Chemistry I talk about that a little bit more. Here's a quick video to show you what I mean by that and why metals are such good conductors of electricity, and then we'll move on to the rest of our list.
The behavior of aluminum is governed by a different kind of force. Aluminum is a metal with an electron cloud of 13 electrons per atom. 3 of these electrons are available for bonding. You can think of each atom as a positive aluminum ion with 3 mobile valence electrons. Aluminum's properties are best explained by a model consisting of a crystalline array of positive ions engulfed in a sea of valence electrons. The particles in aluminum are atoms. but the forces that bind them together are forces of attraction between mobile electrons and fixed positive ions. Aluminum's 3 valence electrons per atom make these forces pretty strong. As energy is added to condensed aluminum, most of it is absorbed by increased ion vibration and electron motion. At room temperature, however, vibrations are not strong enough to break down the metal's crystal structure. This is why at room temperature, aluminum is a solid.
Okay. There's a location of metals on the periodic table. They're to the left side of the staircase. So I'll review the staircase in a minute once I show you where the nonmetals are and what that's all about. So nonmetals, complete opposite. So dull or glassy looking. Think of like a piece of charcoal, like a piece of wood, right? You know what I mean? So those are nonmetals. They're dull, they're glassy looking. They're definitely not malleable or ductile. Like a piece of charcoal. If you whack that with a hammer, it's going to break into a million pieces, right? Or a piece of sulfur is a good example as well. Sulfur is like a yellow, chalky looking rock, right? Very brittle. So the opposite of malleable and ductile go along with brittle that I have here. They don't conduct electricity at all. And they're on the right side of the staircase. Okay, right side of the periodic table. Let's take a look at where that is. And then we'll wrap it up. Okay, so here's where our staircase is. The next slide has a better view of how that looks. But the staircase on your periodic table kind of goes here. All right. Any element touching that staircase, like by touching I mean has a whole like side on it, is going to be something called a metalloid. All right. So we'll get to that in a second. Left side of the staircase, most of your periodic table, and you have that chunk down here. Those are called your intertransition metals. They are metals as well. Okay, so that chunk underneath really kind of belongs up here. That's the left side of the staircase. All those are metals. Right side of the staircase are nonmetals. 2 exceptions here. One for nonmetals. You can see that most of the periodic table to the right of the staircase are nonmetals. You have one exception right here. That's hydrogen. Okay. Hydrogen is over here because of the electrons it has. Talk about that later. But just know that it is definitely not a metal. Okay. So students make a silly mistake on that all the time. Hydrogen is one of our exceptions to that location trend. Everything else that touches the staircase is something called a metalloid. All right. Metalloids have properties of metals and nonmetals. So silicon is an example. If you looked at a piece of silicon, and I might have one in school, it's really shiny. It's really cool looking. So you think, oh, it's shiny. It conducts a little bit of electricity. So like, all right, conducts electricity, shiny, has to be a metal. But if you whack it with a hammer, it breaks into a million pieces. So it's very brittle. So because silicon is, which is right here, because silicon conducts electricity, it's shiny, but it's brittle, it has properties of both a metal and a nonmetal. So we call that a metalloid. Everything along that staircase follows that same pattern. Okay? There's one exception to that. It's right here. You see it's still that light blue color. There's one element on the staircase that is not a metalloid. And that's aluminum. Okay? So 2 exceptions. One is hydrogen, not a metal. It is a nonmetal. And aluminum, not a metalloid. It is a metal. All right? Here's a better look at the staircase. It's right here. Okay? It should be on your periodic table already. If it's not, you can draw it in. This periodic table kind of got fancy here, and they moved part of the staircase over here. But you can see the color coding of this. You have your metals in yellow, nonmetals in blue, metalloids in green. Okay, so make sure you know where those are. Very easy. So I ask you any question about an element, ask you what it is, and you could tell what it is right off of the location. So if you don't know what molybdenum is right here. Easy. It's a metal. If you don't know about selenium, I have no idea. Well, there it is. It's a nonmetal because it's in blue over here, to the right of the staircase. And anything along the staircase, silicon, germanium, tellurium, they're all boron, they're all metalloids. Okay, that takes care of the lesson for today. And hope you understood that. And if you have any questions on it, make sure you let me know. All right, thanks guys.